Yeah, I had trouble finding it this time.
Oh, did you? The icon?
Yeah, it's just my mom's computer is a Windows computer, so it's a little hard to navigate for me.
Ah, okay. That icon looks like this flower over here.
Yeah.
So if you can find that, you should have something like that on the desktop.
Yeah, it's in my desktop folder. There's just like not an actual desktop, so.
Ah, okay. All right.
Yeah. All right. I'm gonna send you some pictures of my stuff real quick. I just
Okay.
can get to that.
This GoToMeeting is a real computer hog. You almost have to have everything else closed out on your system. In other words,
Oh, really?
yeah, if you've got a lot of stuff running at the bottom, your GoToMeeting is really going to go slow. So I try to close everything out. Like right now I have 2 other Chromes open. My computer's, that's going to slow it down. So let me close that one out. So now I'm probably okay. But yeah, definitely when you run GoToMeeting, try to have that being the only thing you're running on the taskbar.
Okay. On it. I'm getting these sent to you right now. There are some things we learned earlier in the semester because I actually got a B on that test.
Okay.
The test that so that brought my grade up from a 48% to like a 59.6.
On this test that we're covering tonight?
Well, yeah, the test that I just took that we were working on before,
Okay.
it yeah, I got a. So this is stuff from earlier in the semester that I didn't understand because my mom, because like we have a cumulative final, so she told me to go back and do things I like didn't
I
understand.
get you. I got you now. Okay.
Yeah, so this is some vocab stuff that I just don't understand, and it's stuff that we've had to know throughout, and I just don't get
All
it.
right. Let's have a look.
I understand the top part, just the continuity.
All right. A good definition for continuous is you don't have to pick up your pencil to draw it.
Okay.
There's a more complicated definition of it, but I don't think you need that for this. A continuous function is one. In other words, I can draw this function without picking up my pencil. I can't draw this one. I can't draw this one. I can't draw this one. All of those I have to lift my pencil to draw them.
Okay.
I can't draw this one without lifting my pencil.
Okay.
This one, they're calling that an oscillating discontinuity.
Yeah.
Oh boy. I've never actually heard that expression. I think it refers to something that oscillates with such a low period that it effectively acts like a discontinuity, even though it does not follow that definition of what I just said. It just oscillates very, very rapidly. If I were to draw an oscillating discontinuity, it would probably look something like this. So rapidly that it creates problems, and so that's why they have a name for it, even though it's not technically discontinuous.
Right.
Okay. A hole, like right there, if you were to graph that on my calculator or computer, it wouldn't show up as a hole. It would look continuous.
Okay.
Because that hole is infinitely small. In other words, that hole is only a hole at one spot on the number line. Well, there's an infinite number of spots just between 2 numbers on the number line. So if there's a hole only at one point, it's not really going to show up on a normal graphing calculator.
Okay.
And it would look continuous. So what they usually do is when you graph them manually, you draw a nice big circle where that hole is, just so that everybody knows there's a hole there.
Mm-hmm.
And then this one here, notice that there's not really a hole. At this point right there, there's another point on the function up there, the black dot. So
Okay.
that's the only difference between these two charts, is that this one, there's actually another value for the function where the hole is.
Okay.
A jump discontinuity, you really have to, not only is there an open circle there, but you definitely have to lift your pencil up to draw this graph. And not removable means there's nothing I can do to remove that. This hole, that's kind of a removable discontinuity because you wouldn't see it on a typical graphing calculator.
Okay.
An infinite discontinuity merely means that on one side of that asymptote I'm going to negative infinity, on the other side I'm going to positive infinity. So it's an infinite discontinuity.
Okay.
All right, let's look at the next page. Increasing, you have any questions about when a function is increasing?
No, I'm very, very lost on boundedness, though.
Okay. If I
still don't understand.
if I draw a sine function, it's bounded on top by 1 and on bottom by -1. Never goes outside of that range.
Okay.
If the function looked like this, it's not bounded on any side. In other words, if it keeps following this pattern out to infinity, then there's no upper bound. There's also no lower bound. This would be a strange function, but still, that's what boundedness is about. If we go back and let's go back a page and look at those couple of functions that we had up. This function here, this continuous function, has no bound on the upper side. According to this graph, these things go up to infinity. But it's bounded on the lower end by whatever this lowest point is. So this has a lower bound but no upper bound.
Okay.
Same thing with these two. Same thing with this one. Doesn't have an upper bound because this thing goes up to infinity, but it looks like it does have a lower bound. Wherever the lowest point on that end of the function is, or this, appears to be a lower bound. Well, this one here has no upper, no lower. We go all the way down to negative infinity. We always go all the way up to positive infinity.
Okay.
This one, the way they've drawn it, it looks like there might be a lower bound, but no upper bound.
Okay.
Increasing just means always going from lower to higher.
Okay.
Let me give you an example. You tell me where it's increasing, where it's decreasing. Let me put some numbers on here.
Okay.
Where is it increasing from?
It increases from 10 to 0.
Negative 10 to 0. In other words, you
negative
always
10 to
read the x-axis when you're identifying where it's increasing. You don't read what the y-axis is doing. We're interested in what we're doing on the x-axis. Well,
Okay.
Technically, we're coming from negative infinity to 0.
Yeah.
So I would say increasing on the interval negative infinity to 0. Also, what? Other interval.
5 to infinity?
Yeah. And it's decreasing on what interval?
From 0 to 5.
Okay. I think you understand increasing and decreasing.
Yep.
Constant, that's a horizontal line. Always. Any constant function, a constant function would be y equal 3. No matter where you're at on the horizontal axis, y is always at 3. Y equal 2 would also be a constant function. In other words, there's no variable. It's just y equals a number.
Okay.
Okay, here's a classic sinusoidal looking function. Notice there's no arrows at the ends. So I can definitely say that that's bounded above by this point and is bounded below by those points, whatever is the lowest of those points. And when you talk about boundedness, you are talking about the y measurement, not the x.
Okay.
Okay. This function here, is that bounded?
Yeah, bounded below.
Only below, not above, but there's its lower bound. Whatever the y coordinate is of that point where my cursor is its lower bound.
Okay.
They don't tell.
Yeah, I guess.
And they label,
I'm gonna try and
B,
find.
but if that B might be the x coordinate. So it would be the y coordinate of B would be the lower bound.
Okay.
This one's bounded above, just the opposite.
Okay.
This one is, you could say that it's not bounded above or below because it goes off to positive infinity there and down to negative infinity there, but there is an interval where it's bounded. In other words, if I wanted to go from just from -5 to 2, it is bounded. It's bounded there on the bottom and there on the top. So you can be bounded on an interval, and that merely means what's the highest point, what's the lowest point on that interval.
Okay.
And that's kind of when they talk about local extrema. That's what they're referring to. Is,
Okay.
in other words, this point right there is a local max because, and the definition merely means that there's points to the left and to the right that are below this. If you have that, you have a local max. And it doesn't matter how many points. It doesn't have to be many. If I have a function and it's going like this and there's a little blip like that, that's a local max. That's a local extrema. Why? Because I have a point right there and a point right there that are below that little peak that I put.
Okay.
So that's all you need for local extremas. So if I draw a function like this, I've got a local extrema here. I got a local extrema here that's a local minimum. I got a local maximum there, and I got a local minimum again there. None of these are absolute. The difference between local and absolute is absolute means for the entire function. Well, for the entire function, the absolute minimum is going to be negative infinity. And for the entire function, the absolute maximum is going to go up to positive infinity. But within this range, you have all of these local extrema, local maximums, local minimums. What does this say as range what?
All range values.
Oh, value
So,
of f. Okay, so the value of,
I don't know. The value of that number is greater than all the other values, so it would be the maximum.
well, it's, oh, for an absolute maximum. Yeah, excuse me. Okay, yes, that's exactly right. The value of the absolute maximum is greater than or equal to all other range values. The local minimum is a value where it's less than all the range values containing C. I don't know what this says, but in other words, there's a local minimum right there. But it's not an absolute minimum. We go to negative infinity over here, and we go to negative infinity there. So it's just within a certain range on the horizontal axis that this is a local minimum. And we have a local maximum, we have another local maximum, and the way this was drawn, this one looks to be an absolute maximum. This looks to be a little bit higher than this over here. Or at least it's higher than or equal to. So you could call that an absolute maximum.
Okay.
Relative extrema merely means local minimum or local maximum.
Okay. Guess that'll make sense.
This one or that one. Well, if it doesn't, let's keep talking about it, because
I guess the thing I struggle with most is boundedness. I struggle with problems where it's not very clear. I'll try and find one in my worksheet, but
well,
I'll try and find one.
boundedness, you could say, is about range. In other words, the reason the sine curve is bounded above and below is because the sine function never goes above 1 and it never goes below negative 1. So I have absolute maximums there, there, there. I have absolute minimums there and there. And the range, no matter which direction I go, it never goes outside of that range. So I could draw a dotted line across there. There's my upper bound. I could draw a dotted line down there. There's my lower bound.
Okay.
Now, if I have a function that does what your function is doing, which comes down from infinity and then does some of this, something like that, well, how's that bounded?
Bounded below at 0.
Right. In other words, at y equals 0 is a lower bound. There's no upper bound. There's an upper bound only if I say in this range there's an upper bound right there. But throughout the domain of the function, it is not bounded above. It goes to infinity in that direction and that direction.
Okay.
So let me draw a few more functions here to make sure that is this bounded?
It's unbounded?
Exactly. Because the highest value is plus infinity, the lowest value is minus infinity. So I can't draw a dotted line on any boundary here. There's no upper bound. If I put my upper bound up there, well, this doesn't take long for this to get on the north side of that. The same thing on the lower end. Yeah, let's see. All right. I mean, these are pretty good illustrations of boundedness, the ones they've drawn here, because both of these, this one's only bounded on one side, the lower side, And this one's only bounded on the upper side, and you can see that from the curve.
Yeah.
In other words, if you think about this in terms of range, well, if you said, what is the range of this function, you'd say it goes from whatever the y-coordinate is of this to infinity, right?
Yeah.
Well, that y-coordinate is the lower bound. In other words, if the range has some limit on either end of it, this function down here is bounded above but not below. This function here is not bounded at all, but it's bounded if you go from the interval from -5 to 2, it's bounded.
Yeah.
There's the upper bound, there's the lower bound. But in function in its entire domain is not bounded. When we talk about the sine function, it's bounded over its entire domain. No matter how far to the left or how far to the right you go, you never go outside those numbers. It's always inside that range, that upper bound and that lower bound. Same with cosine. We draw the tangent function. Is this bounded?
No. I don't think so.
Not anywhere. It's got vertical asymptotes every pi, but it's not bounded at any point. It goes from negative infinity to positive infinity on the range. So when you're thinking of boundedness, you're thinking of the y measurements. All right. You have any last questions? I don't mind going a few extra minutes over because we started a little bit late. The only problem is I do have to get to another session, so I could do another 5 minutes if you needed me to.
You know, I don't really know because we didn't have school today, so it's not like we started anything new. So.
Okay. Are you doing?
Yeah. So I don't really think I need it.
Okay. Okay.
But I'll have new stuff for you Wednesday because we go back to school on Wednesday. So.
Okay. Sounds good. We'll just wait till then.
Okay. Well, sounds good.
All right, Aspen. I will talk to you Wednesday at 7.
All right. Thank you so much.
Bye-bye.